Day 50, Honors Physics, Conservation of Momentum, Problem 29. Once again, this one also brings in some conservation of energy, which is where you start the problem. You have an individual roller coaster car at the top of a tall hill, 12 meters tall. And we're assuming no losses on the way down, no frictional losses on the way down. So the GPE of that car at the top of that hill will transfer to its kinetic energy at the bottom. So this over here represents just that single car before it hits the second car. Its kinetic energy just before it hits the second car will be equal to 1/2 mv squared, equal to the GPE 1. And you figure out then that the initial velocity, well, the velocity at the bottom of the hill will be the 15 meters per second. Once again, you don't even need to know the mass of that car to do that problem. All right, so then for the collision at the bottom, so over here now, this whole segment here represents the collision at the bottom only. We have one car moving. The single car that rolled down the hill has a momentum of 22,500 units. And that is the total momentum of the system before the collision and after the collision. Once again, there would have been a real fast shortcut here, because any time two cars of equal mass strike each other and stick together, the final velocity is just going to be half the original. So you could have taken a shortcut here on this one. But just to show you it in a very thorough manner, total momentum is 22,500 for the combined two cars, which are now then together 3,000 kilograms. So the T here stands for total. Total mass times the final velocity after the collision at the bottom of the hill. So at the bottom of the hill, these two cars will be going 7.5 meters per second. So now what we'll do to go back up the hill, assuming no frictional losses, there is some transfer to heat during that collision. We'll come to that in part B. But now we've got to figure out how high these two cars go. So we're going to use conservation of energy. Let me write this down. All right, so I'm calling the post-collision at the bottom of the hill kinetic energy, I'm calling that KE3. So this KE3 of the two cars stuck together is the kinetic energy just as it starts to go back up the hill. That energy, without losses, will be transferred perfectly into GPE4. So down here at the bottom, I have KE3 equal to GPE4. Once again, you really don't need to know the mass of the two objects. If you plug that all in, you get H4 is 2.8 meters. Now, you also have to figure out part B, how much energy is dissipated in the collision. Simply what you would do with that is figure out, well, we already have the kinetic, well, we didn't do it explicitly. Over here in part A, way over here on the left, we could figure out the actual kinetic energy, excuse me, of the individual car, the starting car, before it hit the second car. So plug in 1/2 mv squared to figure out, well, to actually figure out KE2. And then, yeah, back over here on the right-hand side, you definitely want to then actually figure out exactly KE3, which I'm symbolizing or using to symbolize the two cars stuck together just before they go back up the hill. So you have to actually plug those two numbers in and figure out the difference between those two. KE2, which would be greater, minus KE3 would be the energy dissipated, turned into heat. As a side note, just because I've been using 10 instead of 9.8 and sometimes rounding off to 2 sig figs, sometimes 3, H4 in a perfect world would have been 3 meters, would have been 1/4 of the 12 meters. But the way I was rounding off here, I got 2.8. That's acceptable, so don't let that scare you. The final height will somewhere between 2.8 and 3 meters for the final height of the two cars.